we're going to talk about Newton's third law. And I think unequivocally this is the most tricky law to actually understand properly out of the three laws of motion for GCSE. It's the one that everyone remembers, but actually few people understand properly. And I've actually seen science teachers teach this wrong before. Science teachers who weren't proper physicists teaching this wrong. So let's talk about this and do some examples in a bit of detail so really get to grips with it. So Newton's third law, the third law of motion, is that every action has an equal and opposite reaction. Or the longer version, which you should probably learn as it's more likely to be the definition you would need to learn for most examples, is if an object A exerts an object on an object B, then object B exerts a force of equal magnitude but in opposite direction on object A, or body A. So essentially, what does this mean? What do we need to look at for this? So the common example, and I'll look at the example that I actually saw go wrong. So what this means is that if you push into the wall with 50 newtons, due to Newton's third law, the wall will push back on you with 50 newtons. Okay, now why can this be difficult then? Because this has to be the same type of force. For Newton's third law pairs, they're called, so if you're talking about a Newton's third law reaction, it has to be the same type of force all the time. So let's talk about the example I've seen someone teach wrong. They said that, oh, if you stand on the ground, well, your weight, your gravitational force, maybe whatever, going downwards, let's call it 700 newtons, and then due to Newton's third law, the ground puts 700 newtons onto you. Now that is actually not an action and reaction pair, and we have to be clear on why that is. They have to be the same type of force. So if you're talking about the weight, your gravitational force acting onto the ground, well, that's a gravitational force pulling you down. The Newton's third law pair of that must be another gravitational force. So the Newton's third law pair of your gravitational force is also that you are putting 700 newtons onto the Earth. Okay, so that you're pulling the Earth also 700 newtons, a gravitational force, okay? Well, why doesn't the Earth move like you move? Well, its mass is huge. Okay, it's got a huge mass compared to you. Think of Newton's second law, F equals ma. So, but it is true, obviously, that if you push into the ground with 700 newtons, that you'll feel 700 newtons back. Okay, so where is that coming from? Well, that's where we need to be careful. So if we're calling that gravitational force, well, you would have, if you were falling in the air, you would always have your weight going downwards. Okay, but you wouldn't have a reaction force coming upwards. So if your reaction force actually comes from you pushing into the ground, okay, so when you're in contact with the ground, you have 700 newtons gravitational force acting downwards, and that causes a 700 newton push of your feet into the ground, and then you would feel a reaction force of 700 newtons. So it is a small difference, but it's an important distinction. What were you calling weight there? Well, that weight is causing you to push into the ground of 700 newtons. So this is a pushing force, and then you're feeling a pushing force back. Whereas if we're talking about weight, well, the Newton's third law pair of that is the gravitational force that you put on the Earth, which is the same. It's always the same. The classic example is the moon, that people think that we must be pulling the moon and the moon's pulling us with different amounts because the moon orbits the Earth. Well, no, we're actually pulling each other with the same amount. And it's the same with this, that we are putting the same force on the Earth as the Earth is putting on us. So we have to be really careful with this. Now, you're probably still really confused at the minute, so let's look at an example. A really good look. The best way I found of teaching this is using this example. So let's ignore the Newton's third law first of all, and let's just think of Newton's first law. We said if an object is balanced, that it is either at rest or in constant speed in motion. There's no resultant force and therefore no acceleration. So say you got asked to label the balanced forces on this dog. Let's say that it was stationary, so it's at rest, this dog. Well, you've got the pull of the rope on the dog, pulling it that way. Well, the dog's got friction, stopping it going, which is stopping it and it's balancing out that force. And then you've got weight going downwards, and then you've got a reaction force off the ground going upwards. And they're all balanced. Well, what's the important thing here is that all those forces are acting on the dog. On dog. We may not often label them on the object, so that usually you would just say friction, wouldn't you, on an object? You wouldn't say force of friction on the dog. But when we're talking about Newton's third laws and things, we need to make that distinction here. So this is what you would normally do for a forces diagram that wasn't about Newton's third law. It was just about normal forces, and you'd be absolutely right. You would have labeled the diagram correct, okay? So the key thing is that they were all acting on the object, and they could be different types of force. So for like we were talking with the example of the person standing on the ground, weight and reaction force or pushing forces are different types of forces. So here, weight, gravitational force is different to the pushing force. Now, what would be different if we're talking about the Newton's third law pairs, or the action and reaction forces as they're sometimes called? So let's look at how we'd label them. Well, this is a lot different now. Well, we've got the force on the dog from the rope as before, but also that must mean that the person on the other end of this is feeling the same equal and opposite force from the dog on them. So they are being pushed by the dog, and pulled by the dog, I should say. And the dog, due to his weight, is being pushed into the ground, and the ground pushes back with equal and opposite. So these are Newton's third law pairs. And what you should be thinking straight away is, oh well, why don't those forces, if they're equal and opposite, why don't they cancel each other out? Well, why don't they cancel each other out? Well, they're acting on different objects. One's acting on the dog, one's acting on the other person. It's not the same object. They cannot cancel each other out. So Newton's third laws are always the same type of force, but they act on different objects. Now, if you're finding this quite confusing, if you stick to that rule, you can't go too far wrong with Newton's third laws. Okay, so Newton's third law is the same type of force acting on a different object. So let's use this to try and look at some famous examples. So this is a really famous example. So say you were stuck in the middle of the ocean, and you had a sailing boat but it was a non-windy day, but it just so happens that you've got a fan, and you come up with the genius idea of, I'm going to make my own wind, and I'm going to try and blow the wind into my sail to try and go forward. And you should be thinking, well, would this work? Well, let's think about it. Well, if the propeller is pushing air that way, well, that means there's a push on air by the propeller. Due to Newton's third law, there would also be a push on the propeller by the air, which is pushing it in the other direction. And if we're assuming the fan is attached to the boat, which it would be, then that's going to push the boat in the left direction. Now that air is moving to the right, and now that air is going to push into the boat that way. So this force is the air is pushing on the sail here, and it's trying to push the boat to the right, whereas the same force by Newton's third law is trying to push it to the left. So this would end up cancelling each other out, and this therefore would not go anywhere. Okay, so you should be thinking, well, how would this work? Well, all you would need to do is to turn the fan around. If you've seen those, if you think of the big the boats that they drive around in swamps and things, airboats, and they have that big fan at the back, and the boat going forward. Okay, and that's how they work. They push the air backwards, so there's push of the fan on the air, and due to Newton's third law, they would feel a reaction force, and they're not cancelling each other out because it's acting on different things. There's a push on air, and then the reaction force of the air on the boat. So Newton's third law is actually how everything works. It's just we never normally bother to label Newton's third law pairs because they're acting on different objects. It's not relevant. For this example here, we don't need to know that the person on the other end of the rope is feeling a force. It's not important to the dog, to the object that we're talking about. The same example, another example would be a car. We always say, if we're thinking of normal balanced and unbalanced forces, we would say, oh, well, there's a driving force going forward, and that's maybe going against air resistance and friction, and there's weight downwards, and there's a reaction force upwards. But if we concentrate for a second and think about, well, where is this driving force actually coming from? So if we think of the third law, where it's actually coming from, well, we just call it driving force maybe at GCSE, but where it's actually coming from is the engine's making the wheels turn, and the wheels are turning and they're pushing into the ground. So there's push on ground by wheels, and due to Newton's third law, there is the push on wheels by ground by the third law. They feel a reaction force. So the harder and the faster that they push into the ground, the more that the car gets pushed forward by the ground. If you push into the table, or push into the wall, you feel a bigger force backwards. So these aren't cancelling each other out because they're acting on different objects. How does the car accelerate? Well, as long as the push on the wheels provided by this Newton's third law, which is actually what we're calling driving force, as long as that's bigger than air resistance, then the car will accelerate, won't it? So that would be driving, and that would be air resistance. Now hopefully it's starting to click now, and that's why this is a little bit more complicated than it seems than just memorizing, every action has an equal and opposite reaction. Another example could be, if you're swimming in the sea, okay, so I can't try and draw someone, but when you swim in the sea, you push the water backwards by your hand, so that's push on water backwards by the hand, and you would feel the reaction force forward. If we think of a rocket, okay, well, the rocket jets propellant backwards, So there's push of the propellant backwards due to Newton's third law. The rocket feels that reaction force forward, which gives it its thrust. So everything moves is actually using Newton's third law, except we never normally bother to label it. It doesn't matter that you're pushing the water backwards here. We wouldn't label that. We would just label the green force and we'd call that thrust or something, okay? So all these examples are using Newton's third law. Get used to talking about which object you're talking about. There's the push of hand on water, and then there's the reaction push of water on hand is the Newton's third law. So you need to remember that you don't go into Newton's third law unless they've asked it to you. Stick it to doing balanced forces, unbalanced forces, unless they're specifically talking about Newton's third law. Let's look at an example of a question of this. A very similar question to what came up a few years ago that lots of people struggled with actually. So this was I think it was a 4 or 5 mark question. Describe and explain using all 3 of laws of motion how the motion of the following example occurs. You should name their forces in their respective sizes. So I've given you some help here. Balanced, unbalanced, resultant acceleration, Newton's third law pairs, same object, different object, opposite, equal. Pause the video now and try and use all 3 of Newton's laws that we've talked about in the last couple of videos to explain how this boat would increase in speed. Try and use all of these keywords. So what type of things should we be saying? If you've now answered the question, I've written a bit of a marksy answer below. So the boat is accelerating. It said here the boat is getting faster. Now we know, according to Newton's first law, that it must be unbalanced. So there is resultant force forwards. So we could add here that the thrust must be bigger than the water resistance. Now where does that thrust actually come from? At the minute we probably only scored 1 or 2 marks out of 4 or 5 because we've only talked about Newton's first law. Well, where did we say that thrust is coming from? Well, we said that if there's a propeller or something here, it's pushing that water backwards, and due to Newton's third law, it's feeling a reaction force forward. So the forward force is thrust. This is provided from the propeller pushing on the water. Due to Newton's third law, the water pushes back on the boat with equal and opposite force. So the propeller pushes on the water, and then the water pushes on the propeller with equal and opposite force. What's the second? But we haven't now mentioned the second law. I remember the second law was about how much acceleration there is. So the amount of acceleration would be the resultant force divided by the mass of the boat. And now we've explained using all 3 laws. But the key thing here that people struggle with is this third law bit. People end up being fine with Newton's third law. They eventually learn it, from the reading the revision guide, watching videos, that they get that, whether something's balanced or unbalanced. But people really struggle with what we've talked about here about Newton's third law. If you're struggling still, have a good read over of this diagram example here, and then try and think about some of these examples we've talked about again. Why does a car move? How does a rocket or a boat move? Think about how the forces are acting on different objects.